lecture. This lesson is all about the welding. And there's going to be things like SMAW, GMAW, G. And by the way, if you haven't heard me say it already, I don't always say these correctly. Technically, you actually are supposed to say these out, but I always call them SMAW, GMAW, GTAW, just because that's just what I do. But that is a process, by the way. This AW at the end of every single process, well, most of them, stands for what? Arc welding, right? We're always generating an arc. Why are we generating an arc? What's the point of generating an arc? Heat, right? Because, in essence, what is welding? Just like in the layman's sense, what is welding? What are we doing? We've got two pieces of material right here, and I'm going to stick a plate right here on top of another plate, and I want to join these things together. What are we essentially doing by welding them? Do what? Fusing them. You're melting these two down in a zone, and you're getting that material to mix. Now, in many cases with welding, we're also adding a filler material, right? We're adding material into that joint to help bind it all together very well. And typically that filler material is ideal to match whatever we're welding. But it's all about heat. I mean, you look back in the day before we actually had our arc welding process, how did they build, you know, think back to your ironclads, Civil War ships. They didn't have the arc welders out there. How were they binding all that stuff together? Do what? They did bolts, but they also actually had another process. What else? Huh? They had that, but there was actually a metal binding process. They actually used to use a chemical reaction. I can't remember, we demonstrated it in, well, we had a chemistry class that they demonstrated for us, like in Physics 1, or Chemistry 1. And it's basically a chemical reaction, but they would use a super, super hot reaction to actually weld ship plates together. So they actually had it, but they weren't doing it the way that we think of it. They weren't running electricity, they were using chemical reactions to essentially melt joints. Obviously very expensive, and they didn't do it all over the place. They obviously used rivets, those kind of connections. But shipbuilding had welding forms prior to our typical arc welding. Now, our arc welding system, except for acetylene, of course, is typically based on the flow of what? What are we moving to make all this heat happen? Electricity. Positive to negative. We're moving electron flow. And that arcing effect, where we're jumping from a positive to a negative, with that little lightning strike, if you will, gives off a lot of heat, right? So in that reaction, we start melting all this down. In this case, in the case of stick welding, or SMAW, we're also melting down some of this filler material in the rod that joins with it and does that. Now, we've also learned in the welding process, though, even though, let's say, we've got this electrode right here, and we've got this plate right here with a negative component, and we have this arc going on, and we're melting some of this filler into this situation to help join. What happens in this zone right here that can interfere with the welding process? Okay.
Oxidation.
Elaborate. Just in general, you have stuff that can possibly get into the middle of the weld, right? Impurities, contaminants, stuff like that you don't want to happen. Now, what happens to the weld if we start getting a lot of things flowing into its process? Exactly. Porosity weakens it, so we don't want that. So to protect this weld, to keep it safe while it's doing its thing and this filler material is moving from the rod to the new place, what do we need to add? Some kind of shield, some kind of thing to actually protect this zone, to say, okay, different air particles, things in the air, you can't get into this zone because I am creating this bubble, this shield, typically of gas or some other material that's actually protecting it while we move along. Now this comes in a lot of different ways. We can actually do it with, in the case of SMAW, we can actually have our rod with the filler material in the middle, the material that's actually going to be there at the end of the day joining with the other metals. And you have this component on the outside of the rod they refer to as flux. Okay? So, when the electricity flows through, we have the arc, there's the explosion, everything starts to get melted in this process, what does the flux become? Well, that's true, but it's actually, it creates its own shielding gas component too, as it actually happens. But it does leave slag at the very end, absolutely. So that's a residue associated with the actual ethanol process. But essentially, the rod is the combined effect of having both at the same time. You get your filler material, that would be A. You get your flux, B position here. Both are consumed. One is a shield, one is the actual filler. And it protects your weld. Now you go into the science of in terms of how fast you move and all those things, and that's kind of beyond the scope of this course. But the key thing is you understand that you got to have that protection along with everything else. Any questions so far? So how many have done stick welding before? Yeah, a lot of us. A lot of us have that experience. So many hours spent just learning how to do a little arc welding and striking it just right. And of course you also have your safety gear, your protection equipment that you have to keep going. Now, one common thing, I don't even know if we even address this in our safety issue, but obviously, just in case nobody knows, you don't need to be welding in a wet zone, just in case that's not ever explained to you at any point in time. Since you have all this high amounts of electricity, don't be welding in a puddle of water, all right? Just in case no one ever tells you that from this day on, and you didn't know that, don't weld in water, all right? Now, there is underwater welding, but that's a whole different process. So, I just thought I had the urge to say that. Sorry, don't weld in water. So anyway, so we've got these little devices, and the welding system's been around for a long time, especially SMAL. And you've got a pretty simple setup. You've got a box, you've got whatever you're going to weld, you've got a clamp, and both of these hook into the box. And the box typically hooks into what type of voltage source? AC, but also what voltage, how high voltage? Yeah, you're basically in the 200s, you can go 220 to about 240 is your hit point. You can go three-phase, 2-0 sometimes. Different machines go for different ones, which is obviously different than the good old-fashioned 110 voltage that you're used to seeing on your wall plugs, right? Although, don't get me wrong, I think you can actually go buy like a 110 voltage arc welder. It's just basically not very good, but might be able to work on a few little things. So you'll notice that on most of these SMAL systems, so you plug it into the wall there, you've got your electrode and your rod here. By the way, is there only one type of rod, or are there multiple types of rods out there? Multiple, because you got different materials, different fillers, that kind of thing. You got your clamp, where the electron flow wants to happen, but you got this dial. You got this dial on your SMAL unit. So we're going to go SMAW right here. What does this dial control?
Your amperage.
Amperage, not voltage, right? You're still running the voltage, but your amperage. Now here's the one thing you want to make sure you understand and just take with you. So this system basically has, the voltage doesn't change a whole lot, but the amperage does. So what do you think happens? And basically, describe what amperage is for me.
Flow of electrons, the amount of electrons.
Right. So it's like how much you're opening the water hose up. So if you got a water hose, you can get a little valve on the water hose. You turn it on just a little bit, you get a trickle of water, right? You open it all the way, you get a flood of water. A bunch of water molecules are flowing. Same thing with amperage. Now, does the pressure of the hot water hose change? No. Let's say your hose was running at 80 psi. No matter if you've got that valve open or closed, the pressure behind that hose is still 80 psi. The pressure at its hookup point. Now, your flow changes, but the pressure doesn't. Technically out here the pressure does, but we're talking about in the hose. So that's kind of what we're talking about here. We're going to change the flow of electrons. We're not really shifting around the voltage that much for SMAL process. So you're flowing lots of electrons, which of course if you're flowing lots of electrons probably means you're flowing a ton of heat, right? So what's the risk though? Why don't I just crank this sucker all the way up to max and just burn through those rods? What goes wrong? Right, you're just going to overheat your part and you're going to melt too much. Although melting is what we're after, you can do it too much. And if you've ever actually had to try to recover from burning a hole through something, it's not very, very easy. You can keep trying and some people can do it. I'm not one of those people. So when you burn through, you got problems. Questions so far? All right, so you got plenty of experience on it. You kind of know what we're talking about. and you got a lot of confidence there. So give me some examples of some welding rods. Let's say we're talking.
10,
All right, so 60-10.
60,000 pencil string.
Okay. Now let's stop for a second. Why 60,000 psi or KSI? 60 KSI. Why 60 KSI? What's going on there? What does that make you think of? Stronger as which type of metal?
Kind of metal you're welding.
Well, all right, let's think back to our previous lesson. What was you had different grades of steel, right?
36.
You got a 36 KSI, right? And then you got a 50 KSI. Right. So, clearly, we don't want to use a rod system that is weaker than our actual base material, right? That just totally makes sense. Now, they've got it at 60 KSI. The reality is, our steel typically doesn't get up to that value, most of the time. But that's okay. As long as we're going stronger than our base material, we're technically good. And there's a lot of things, the imperfections that go into the welding process. It's a manual process. It's very explosive sort of in nature. So uniformity across a small scale is not really true. In fact, in the welding science, we have a lot of things that happen. We're actually burning through, we're melting metal, we're adding filler in. We don't necessarily have a perfect uniform cross-section in this design. So all of that factors in. So a little bit stronger material is a great thing. Now, this is a very common welding rod size. And if a person wanted to learn a little bit more, we could always just do welding rod sizes. Because once again, everyone wants to make it useful for you to find what you need super fast so that you'll buy their stuff. So you could actually go through welding rod. Let's just see what we got here. And as you all know, they all show up on the actual welding rod, and you can see, what's this color I'm seeing right here? Is that the filler? It's the flux, right? Yeah. And obviously you're seeing a different coloration between this flux and this flux. What do you think is going on here? I believe they're both 60-10. Any ideas? It could be dyes, it could be specifics. Oh, here's a 60-13. Could be. So the composition of the flux obviously can change too. And once again though, no one's going to be selling products without giving you some information to work with. So they're going to explain to you or have diagrams or whatever the case may be. There's a good one. And again, what's the flux for? At the end of the day, what is the flux for? It's protection, right? So if I'm doing the situation where I need like better protection, I mean I cannot have any contamination in my weld, I'm going to want something that has a very, very uniform, a very gaseous result when it burns through. So flux changes can be part of it. So we've got 60-11, 60-10, I think that's the 70-18. Yeah. So you've got lots of different options, all having different properties. Even the actual amount of filler size is different. But again, it's okay. You don't actually have to know a huge amount about it because you can always look up the data that you need based on your scenario. And of course, different results. You have different types of weld, different styles, different circular components, again, beyond the scope of this course. Apparently that's in Russian, and we don't have to worry about that. 60-11, another very common size. And what is the drawback, though, for SMAW? Give me some negatives. I'm out here, I've got my piece of equipment.
You got to carry a lot of weight and consumables.
All right, you got to carry around stuff. Doesn't roll around. You guys supposed to have them in your pocket, right? Now, the protective gear, the PPE, personal protection equipment, is about the same for most of these processes. Most of the arc welding. You still got to protect your skin from the ultraviolet effects. But you've got this piece of equipment, and SMAW is great. You've got this box, you plug it into 220, or a generator. You've got essentially two components coming out of it, a clamp and your rod holder. So why don't we just use this all the time? What's the drawbacks of S-Mall? So you got to carry some stuff around because you got to carry, your pocket full of sticks. Okay, it's not good. It has problems with thin metals. There's a good one. So with S-Mall, you have that slag problem, right? So you got to turn around and you got to clean it up, and that's always annoying.
Electrodes are a lot more expensive than they were.
Yeah. So you basically, and let's actually focus on the electrodes for a second, the rods. In terms of actually getting the job done, what is a big drawback of having that stick on there?
You have to stop and change your stick and it leaves gaps in your welds.
Yeah, more ways, because you don't always get it all the way down to the nub. You always have to stop and replace and keep going. So you have to interrupt your process to change out the stick and keep going. Although the process itself is nice, equipment-wise, having to change that out really interrupts the flow, and therefore the economics of it aren't great. So,
You have to clean your wheel area.
yeah.
Connection.
That's true. That's true. Sometimes you might have to stop before you can even throw the stick on there and clean off slag and those kind of things. So we got slag cleanup. We have a slow stick process. But this is why S-Mall is actually very common in your mom and pop shops and those kind of things. Folks that just have a welder maybe on the farm, because it doesn't take a whole lot of skill to use, and they're not necessarily interested in rapid production. Okay. Now, don't get me wrong. Do what?
You really can't automate it either.
That's true. Yeah, it's true. You basically have to switch. You can't really have the robotic. It's just to be a waste of time. I guess somebody could make a robot that actually swaps out the stick and everything, but that would just be kind of unnecessary considering we have some of the other processes available to us.
The idea of like, especially farm equipment, if you're like plowing and digging in the ground, you got to have a high tensile strength for that. So
That's true.
this is upside to it versus having something.
That's also true. You do actually have a lot. Typically, this gets used on a lot of heavier fabrication. Case in point, outside, absolutely. So, like your actual architectural stuff, S-Mall is the way to go. We don't throw MIGs out into the field erecting structural steel. Well, we got this kind of stuff all day long.
Big wheels going to hold up to a high
Yeah.
pressure.
Emission, anything with pollution, gas, oil.
That's also true. You also have the condition of, and that's one advantage of this, we don't have to worry about shielding gas with tanks and those kind of things. So SMAW definitely has its place. Absolutely. It typically ends up being in large, heavier materials or non-high process needs. We're doing repairs, it's great for repairs. We're doing, agricultural products, great for that. Although, don't get me wrong, I know plenty of guys that got some MIG welders too in their farm shops as well. But it's the starter. It's where you get going and get your technique down. But the limitations brought upon the need for the GMAW, which of course stands for what? Yes, metal, arc weld. So, essentially, as you're probably well aware of from process, we swap out some stuff. We still got our good old-fashioned clamp down here. But we swap out with a more elaborate head system, a little motor in here that feeds wire into this, and of course we have a tank on the back. Also often referred to as the MIG welder, right? So walk me through this. So I know that I've got this tank here that creates the shielding gas, and it is pumped through into my handle. And if we can pull up a good image here, MIG welding. See a nice little icon. I was actually wanting to see one of the, there we go. So we've got this nice little image right here, MIG welder head. Why we got this big opening right here?
That's your gas.
Yeah, your gas flows around the extrusion of the wire. So here's your filler, gas is coming into the space, does your shielding effect, everybody's happy. Negative side, of course, or not really negative, but what do you have to be aware of in terms of the speed of this wire?
Your amperage, how your wire speed.
Yeah.
Your voltage.
Faster you roll, the narrower the bead.
Yeah. So your movement is a factor. How much, your control, your settings is a factor. The actual direction you're actually moving in will control your speed. So you got to be aware of the wire speed. You got to be aware of the material choices, and once again, there's going to be plenty of charts for you to line this with. So, what do you have to worry about though in this zone?
Splatter building up and
All right, so you basically, you get a little splatter into this zone right in here that interrupts the flow of the shield gas.
So we clocked up with, they'll say they either replace it or keep it clean.
Yeah, you basically, and of course these heads can be swapped out pretty quickly and effectively, but you just got to be aware of that, because the moment you start getting zones of your shield gas not flowing correctly, you get what on your weld? What happens to your weld? Impurities, right? It's basically, that's when you get the problems that are starting to occur. So obviously keeping the equipment clean. Now you have to really worry about that with, SMAW, because there is no head to kind of keep clean. So that's one of the negatives. Also, let's just face it, you've got more things to go wrong. You can run out of gas and not realize it. You have a motor system in here. You can have a wire get kinked. All kinds of things that, since we have more moving parts, you have to be aware of. Which is one of the other reasons we don't like to actually have to, if we're going to do field work, we want to have simple equipment versus more things to go wrong. And as you mentioned, let's look back here. If a nice breeze is blowing this way, what happens to that gas coming out that nozzle? Blows right along with it. Again, always going back to that problem with the weld and its impurities and it being impacted by the outside environment.
It's not good for outside at all.
Not really at all. Don't get me wrong, plenty of people do it, but you can lose weld strength by invoking it outdoors. So one of those things to keep in mind. Or if you just happen to be running right next to a gigantic fan in somebody's shop, that might actually be a problem. Although we typically provide ventilation, we don't want a lot of super high ventilation right next to the MIG process. All right, questions so far? Now, we've often, it's again, safety is always there, so I won't go into that whole lot of detail. But your basic equipment includes what for safety? What's your protection equipment?
Helmet.
Got to have a helmet on it. Now, does it have normal glass on it or not?
Oh, what now?
Does it have normal glass or what?
It has a dark.
Has a filtered glass, right? Yeah. So you got a helmet. Got to protect your skin. You got to have your gloves on. Good. Now, why can't I just wear my flannel shirt and protect my skin with that? Hey, yep, and you can catch on fire. That's always a fun thing. So I remember some of our guys in high school, they would brag on how many times they got burned. And he's like, I got burned here and here and here and here and here. And he was proud of it. So I didn't understand that. But he wouldn't wear his gear for some reason. He enjoyed the burns, I guess. Woo, that is a good one. Man. Obviously don't wear shorts. And typically, although your feet aren't exposed as much, boots are obviously part of the process because you can easily drop some stuff on them because basically you're dealing with molten metal all over the place. Now, let's say that you, however, are on the safe side. You're one of the folks that have figured out, you know what? I don't have to sit here and weld this thing all day long. I can get a robot to weld this for me. So here's our robot arm. Got our MIG on it. So what's your safety requirement now? Well, you basically got to find out, first of all, is that filtered glass or not? So if it's not, you better put your helmet back on. And typically, if this is, in reality, even if you pretty much have to cover all your skin again anyway, if it's not fully filtered. Now, will this box particularly have filtered glass? Yes. And it'll probably have a tube coming out of it where something goes through here. What is that? You're basically going to ventilate, right? You're going to suck all that and get that outdoors because we don't even breathe it in. Well, it just depends on different scenarios. I mean, we've seen these actually out fully in the open, and that's where you see those welding screens, right? So you can actually have a big giant robotic arm throwing some welded things out here in space, but they'll put sheets around it, and they will still get some ventilation to suck all this out. Now, is it going to be high velocity exhaust? Not, otherwise you're going to lose your shield gas. So keep that in mind with this process. Okay, so robotic welding, it's still welding. It's still typically, would you call it, obviously, it's not SMAW because the robot's not changing out the stick. So what process would you typically say robotic welding was?
Yeah.
Gas metal, right, GMAW, right? It just works well. And you look at any factory and look at some of the ways that we're actually doing heavy equipment. You know, your Caterpillar equipment, your big buckets for your tractors, those kind of things. They're still doing robotic welding. And also, they're using MIGs, even though it's thicker material. Is that a problem? We're doing heavy construction stuff, but we're using MIG welders to put them together. Is that a problem? Yeah, not really. As long as you actually account for the right amount, right settings, the right material, you're still good to go. So keep that in mind. All right, questions? So those are the ones you're all probably familiar with. However, there's some stuff that has a little bit more capacity to it. And this is one of them. What's that one? Ever seen that one before? Flux core. Where essentially we are reversing, well, it's actually similar to both, it's mostly similar to gas metal, but it has some similarities to S-mol too. For example, flux core does this. It still feeds a wire, but that wire is sort of unique. For example, the wire, and here's A component, here's B component, and this is the wire. The B component is actually not the flux now, it's the filler. Hence the term flux cord, because A, of course, is the flux. So, let's see if we can get a good picture real fast. Flux cord. Alright, lost internet connection. Awesome. Okay. Looks like our internet just went down, so I'll take... Somebody forgot to pay the bill, so it's just back to good old-fashioned sketching. So we're still actually running a wire through the system, but flux core comes with the advantage of you might have a gas shield on top of this, and you might not. Because since you've got flux coming out with the wire, you actually can produce without having a shield of gas. And one of the things you want to watch for is whether someone gives you a dash S or a non-dash S. So if like you see a welding symbol that does this, by the way, do any of these processes have an impact on that symbol right there? You know, not really. You can. This is the welding symbols, the symbology essentially stand alone. You might actually have a difference of SMAW, GMAW, SCAW. This is where the process, or whichever type of welding you're going to do, is shown to you, but it doesn't have any impact really over here. Nothing significant. But let's step back for a second. FCAW dash S. What do you think that means? What? Hang on. Sorry. All right. So this is your shielding component. So this is where you make the call, do I need gas? Do I not need gas? So when you see the S, it means self-shielded. So therefore, you don't need the gas, right? So when you just see it by itself, you do need the gas. So that's what their dash S is, self-shielded, so the wire can handle it themselves. I don't know, but you got what I'm going for. So self-shielded is one of the things you want to watch out for flux core, because it has the option of gas or not gas, all right? Because it built in. Now, what do you think about the wire, though? So we're talking about a MIG welder to start off with, and how big is that wire? Would you all say millimeter-wise? You're going to just guess, huh? 1.2. All right, pretty small, right? Would you say the flux core wire is about the same size or bigger? Bigger. It kind of has to be, right? Because you essentially have two things going on. You've got your flux as part of it, and you got your filler there. Now, what would you say about the equipment having to push that wire? Is it going to be about the same size as the MIG, or more heavy duty, more robust? What would you say? Well, concept-wise, it's there. But typically the equipment itself has to be a little bit, you have a stiffer wire to deal with, so maybe your gears sometimes bite down a little bit more. They might have a little bit more torque because you have to push through. Concept-wise they're the same, but they do have to be a little bit beefier for most flux core. Yeah, adjustments are accounted for it. Process-wise, the equipment kind of looks the same though, in some sense. All right, so that's flux core, some of the key concepts there, included in the material. We'll stop, that's a good stopping point. Unless there's any other questions? All right.